You see my slides up here?
Perfectly. We
Okay,
can see your slides. And let me say again, Mike is from the University of Nebraska. He is presenting a work in collaboration with several co-authors, and specifically his talk is dealing with the identification of properties in heart failure,
Right.
the preserved ejection fraction. So please go ahead, the stage is yours, and looking forward to your talk.
Well, thank you so much to the organizers for inviting us. This is a collaboration between myself and Professor Tim Seckham. I'm a cardiac surgeon at University of Nebraska who has a longstanding interest in dabbling in mathematics with Professor Seckham, who's a mathematician at the University of Arizona. And we spent the last 15 years or so working on a mathematical model of the heart. What I'm going to talk about today is really an application of that model. Many of you, or probably most of you, are familiar with heart failure with a preserved ejection fraction, also known as HFpEF. It is a form of heart failure that affects millions of people in the United States, but it's one where the contractile function of the heart on surface appears normal. What we're learning here more recently is that this is probably a very heterogeneous disease. It may not have just one mechanism. People define this or talk about this as having different phenotypes. When they say that, they're talking about the mechanisms that revolve around things like LV diastolic stiffness, which is where the disease was originally described, but we're now learning that these patients also have problems with their right ventricle contractile function, diastolic function of the right ventricle. Some patients seem to have problems with the pulmonary vascular resistance. There's probably a bit of an unmasked LV systolic dysfunction. And of course, the patients who have hypertension, which are a large percentage of these patients, have some form of afterload mismatch. The problem with the disease, of course, for us who are clinicians dealing with these patients is that there have been over 25 randomized clinical trials that have, of course, spent millions of dollars trying to figure out if some of these drug therapies that work so well for patients that have a reduced ejection fraction, if they would help these patients. And there actually are no proven therapies. So patients show up in the clinic and we really have no way to treat them. So what we're proposing to do here is to utilize the type of non-invasive data that we get on these patients, so principally echocardiography, along with some other non-invasive data like their blood pressure. And to couple it with our computationally efficient mathematical model, what we're hoping to do is to identify, using parameter estimation, these basic circulatory system properties in the patient. And then the long-term hypothesis is that these circulatory system properties will be able to be statistically characterize different phenotypes of the disease, and hopefully we can then pinpoint patients into specific clinical trials based on the underlying mechanism. So that's the long-term work here. Echocardiography is obviously something that's obtained on nearly every patient with heart failure. The important thing that I want to bring out about echocardiography is that there's an enormous wealth of information in what we call the signals of echocardiography. So there's time-dependent volume information about the wall thickness, of course, a lot of information, more two-dimensional information about the strains, or even three-dimensional image about strains. And then, of course, a lot of information about blood velocity across valves. So this is all information that we can utilize to better characterize the underlying properties of the heart. Along with that, in order to get these properties out, we need a mathematical model. This is the sort of characterizing or defining feature of our model that's different from what you might have seen with, for example, finite element models, is that this is what we would call a reduced order model, meaning that the three-dimensional LV model that you're seeing uses 10 degrees of freedom to describe the kinematics, whereas the axisymmetric model that you see over in the corner over here uses three variables to describe the base to apex motion of the heart, the twisting motion, and the contraction. So that means that it runs very quickly, which is of course useful for analyzing clinical data. I hadn't originally thought I would describe too much about the model, but then I had been looking at the conference and seeing that there's obviously a lot of highly sophisticated mathematicians and engineers in the audience. So I thought I'd give at least a very brief description of the underlying sort of philosophy of the model. We sought out to develop, as opposed to breaking the model up into elements like you would do in finite elements, to describe a global mapping that uses parameters. And it's a volume preserving mapping. So we do this in prolate spheroidal coordinates. And of course, the very definition of volume preservation is that the determinant of the deformation gradient tensor is equal to 1. And if you write out those determinant terms, you end up with a lot of partial differential, you end up with a multidimensional partial differential equation. That's not really very tractable. And so what we did was to make a number of very simple assumptions, which actually turn out to allow a lot of variability in the motion of the heart. So the set of equations you see here would be some of the simplifications that we made to develop the axisymmetric model. So if you let one of the coordinate systems in the reference and the deform configuration be the same, and you still allow twisting or torsion of the heart, we allow the focus of the ellipse to be able to move for base to apex motion. And that simplifies that long set of equations into what's really an ordinary differential equation in terms of the mu coordinate. And then this turns out to be a separable equation that you can integrate directly. And that yields a analytic equation that we can solve. In fact, it's a cubic equation. This term, which is the constant of integration, can also be manipulated to give us the exact type of deformation that we want in terms of some other parameters. And this is what leads to the volume preserving mapping. This is a lot of information in a short period of time, and we have 3 or 4 publications that you could review if you were interested in the details. This is then substituted into a variational formulation that would be very familiar to most of you, similar to what you would do with a finite element calculation. It is a weak formulation. We do full finite elasticity. We represent the passive elasticity along with a helical arrangement of fibers. So very interesting to hear Dr. Corner's presentation today, but we allow a helical representation of the fibers based on actually observed fiber data. And then we have tissue viscosity based on a fairly simple Kelvin-Voigt model, and then active force generation that allows for the length tension as well as the force velocity relationship to be represented. Of course, the surface tractions are in the model. One thing that's unique about our variational formulation is because we have enforced incompressibility right off the bat, we don't have to have additional terms like Lagrange multipliers that make the equations very stiff. We have a full circulatory system model, which is a closed loop model. It has the spatially resolved left ventricle model, and then simpler models, although still spatially resolved, spherical models that describe the contractile force, the passive stiffness of the left atrium, the right ventricle, and the right atrium. And then there's a lump parameter system that describes resistances and compliances in the pulmonary and systemic circulation. And one thing that's a bit different about our model as well is that we have a one-dimensional model of the aorta that allows wave reflections. And so we can utilize these parameters as well. The important thing to note is that all the properties that I'm going to talk about, meaning contractile force, stiffness, resistances, impedances, are all represented by this diagram. So the point then is that in these patients, we're going to have echo signals, which would be volumes, flows, velocities, strains, etc., represented here. So this would be the volume, this would be the flow across the mitral valve by echo, and here in the model. And this is an example of the strains that we measure in the patients and the strains in the model. And of course, what we're trying to do is optimize the model minus the echo observed signals, with the unknowns being the properties that I just mentioned in the previous slide. When I talk about properties and parameters, it may be a bit confusing without a little description. There are actually 70 parameters, 70 plus parameters in the model that describe all these variables. That's obviously not a tractable problem in terms of parameter identification. And so we've focused our attention on the idea of properties, which, as you can see here, are some mathematical relationship that we can define between the parameters in the model. So in some circumstances, it may be very simple. Pulmonary vascular resistance, for example, might be a sum of the actual three parameters that define the resistance in each of the compartments, whereas, for example, in afterload, where there's a more complex relationship between the taper of the aorta and the compliance, we may have a different mathematical relationship. But at the end of the day, we're trying to get essentially one variable out of the parameter estimation, which would be the afterload or the pulmonary vascular resistance or perhaps the left atrial function. And then the long-term idea is that this will define different types of phenotypes in these patients. So of course, when you do a parameter estimation, you're always going to start with simulated data. If that doesn't work, you're probably in some trouble. So this is a simulated data looking at different properties. We've got parameters and properties that reflect contractile stiffness of the ventricle, of the left ventricle, stiffness of the left ventricle, and of course the same properties in the right ventricle, right atrium, and left atrium. There are impedance properties, and then as well resistance properties in the different circulation, or excuse me, in the different parts of the circulation. You can see that in this simulated example, we're able to converge to the known values. We can do the same with noise in the data. So at least at this level, we're able to solve the problem. Of course, that doesn't give us full confidence that we can identify these properties. So we have utilized porcine models of HFpEF, two specific models, one a pressure overload model, which is a banded aorta model described by Charles et al., and then a medical model, which is one that we have not utilized but are interested in utilizing, where we give the animals a corticosteroid, and they develop stiffness and increased pulmonary vascular resistance. So in the banded model, we have utilized the echo data on the pigs, done our parameter estimation that we've just talked about using what would be the non-invasive data. And then at the same time, we've directly measured the properties in the animal. So here is an example of doing ex vivo stress strain testing on the left ventricle of one of these animals with the fiber and cross fiber stiffness. We do pressure volume loops so we can get end-systolic pressure volume relationships as a surrogate for contractile force. We use pressure flow wires so that we can measure the flow and the pressure and get a better characterization of the impedance. And then we can directly measure properties of the aorta as well, based on the taper, and also we can measure the compliance of the aorta by doing direct testing. When we do that, what we find is that if we estimate the parameters using the in vivo estimates, then we get a set of parameters. If we do it in the same set of animals, and we do mechanical testing, we get a different set of parameters. And you can see right off the bat that these are different by about an order of magnitude. And these are the curves over here. And you can see if you look at them on a larger scale, they are quite different. And that, of course, is a bit concerning. However, if you look at them in what's probably more of a physiologic range, which is about a 10% strain in diastole, you see that actually the fiber and cross fiber curves predicted by these very different set of parameters are actually quite similar. And more importantly, when we look at how they predicted pressure volume loops in the animals as compared to those we measured, the blue being what we actually measured in the animals, the B being the pressure volume loop that was predicted by the in vivo parameters, and C by the ex vivo parameters, they're actually fairly similar. So at least for LV stiffness, the basic idea is that these properties, despite very significant differences in the parameters, can be quite similar. So just to finish up here, we did some very initial analysis using some data from a previous study that we had done. So we had a pilot study of patients. There were 10 HFpEF patients and 11 control patients, or normal volunteers. We actually, in this study, we're looking at the strains, but we also had all of this time-dependent echo signals from the controls. These are just examples of the maximum variables in this table, but we had all the time-dependent variables. In fact, we used about 25 of the time-dependent variables in order to estimate the model parameters. What you can see here was this initial attempt to measure the properties that I had mentioned, which were the force and stiffness in each chamber, the impedance of the aorta, the vascular resistance in the pulmonary and systemic circulation between the HFpEF and the control patients. And what we found, and again, this should of course be interpreted as preliminary data, was that in this group of patients, they seem to have more of a pulmonary vascular resistance type phenotype, in the sense that their RV stiffness and their pulmonary vascular resistance were much larger when you compared the HFpEF ratio to the controls, as compared to what most people would think, which is the left ventricular stiffness, which was about 2.5 times greater in the HFpEF patients. And surprisingly, in this group of patients, the aortic impedance and systemic vascular resistance were not substantially greater in the HFpEF patients. So again, just early data that looks at how this algorithm might be applied to identify different phenotypes in HFpEF patients. So in conclusion, what we've found, at least in the early analysis of our foreseeing data, is that we may get very different parameters, but that these do define specific properties that we can identify. And in the human studies, we found some changes in right ventricular stiffness and pulmonary vascular resistance that were out of proportion to what we found with respect to the LV stiffness and the afterload. So in the future, obviously, there's a lot more that we would need to do here in terms of validation with the animals, and then we have plans to do a larger patient cohort. So appreciate the opportunity to present our data.
Thank you very much, Mike, for a very, very interesting talk, rich of details and hints for discussion. Can you hear me?
I can, yeah. So I'm going to stop sharing. It's okay.
We have an echo, I guess, and some noise during the talk, but it was not able to affect your presentation. We have questions from the audience. If so, please raise your hand. If not, well, I can kick in. First of all, I'd like to say that I much appreciated your talk. It seems that with relatively simple models, you were able to give provide a very useful models to able to match the reality, the clinics, and the data. If I understand correctly, you basically developed a simplified three-dimensional model for the left ventricle by using eigenvalue analysis, and then you basically carve out eigenfunctions for the displacement. The first, if I remember well, 10 to 20 modes, and then you couple it with a zero-dimensional model for the rest of the circulation and the other chambers. My question is the following. Did you try to perform some sensitivity analysis and which tools you used, regardless, let's say, of the clinical data, and which tools you used And if in this sensitivity analysis you included the number of modes that you used for the three-dimensional model. Thank you.
No, I appreciate the excellent question. So the answer to your question is that we have done some sensitivity analysis. With respect to the second part of your question, with respect to the modes, Brian Hong, who was a PhD student with Tim Seckham, did a publication where he actually did some very nice work looking at modes and how well he could predict MRI images. And that's where he came up with the idea that in the 3D, about 10 modes gave us about 80 to 90% of the ability to track an MRI image. So that's a little bit of a sensitivity analysis with respect to the kinematic variables. With respect to understanding the outputs of the model, we have done I would say, somewhat of a preliminary sensitivity analysis. For example, we would change the stiffness of the left ventricle and see how that affects the flow across the mitral valve. So that's one example. And that's actually very important. I mean, as you bring that out for parameter identification, because of course, if there is no sensitivity of the output variable to the parameter, then there's no way you will identify it. And one thing that we have found is, as an example, we cannot identify right atrial stiffness unless we use the tricuspid valve flow. And so the flow across the tricuspid valve, actually, because our models explicitly include the Bernoulli principle and inertia, actually provide information about the dynamics and the forces in the chambers. And so if we don't include that and the full time-dependent flow curve across the valve, then we can't identify the parameters. So we have a lot more work to do to fully understand all of these things, but that's just some preliminary work.
Thank you. Questions from the audience? Well, if not, I profit from your availability to ask, let's say, a more general question, which is the following. So there are some parameters that are very important, and so these are related to sensitivity analysis. But then basically there is no way to get their value from clinical data, because measurements are not made, or for example, measurements are very precise. Okay, so how robust can be this approach to parameter identification when you have data that is of low quality or missing at all? So what are your let's say, what is your opinion about this, and how much this can affect the outcome of the numerical studies that people is tending to bring forward? Thank you.
Yeah, it's obviously a critical question, because the clinical data is not only noisy, it also is missing important pieces of information, et cetera. So that is a challenge. And that's why we have tried to focus on the porcine validation studies, because then we can actually directly measure those properties. As one idea that we have going forward, to answer your question specifically, we want to measure the same properties in these animals using echo and MRI, as well as some invasive like pressure volume loops, and then do the estimation of the model parameters using both data sets, MRI and echo, and see how they differ. So that would be one way to get at how the uncertainty in the echo data affects the parameter estimates. So we have some plans to do this type of analysis. We've actually done some MRI studies in these animals, but I have to say we haven't so far done that detailed analysis. But I think that would be one way to get at it. And then, of course, in human studies, it even gets more complicated. And I think what we're looking at is how, the question is how accurate can we get these parameters? And I think if we can't get them accurately in the animals, then it's going to be hard in the humans. But we're just at the sort of early stages of making those determinations.
So thank you again, Mike, for sharing your opinion. And of course, it's a topic that we should discuss for a while, and would like to do as well, to have this discussion more time.